This lesson deals with supplemental problem 4.3. You can find this problem in the course ebook in the Chapter 4 Supplemental Problems on page 2. Given the circuit with a voltage source and a voltage-controlled voltage source, can you find this current I of t in steady state? Let's use our three-step algorithm. First step is to transform the problem from the time domain to the frequency domain. Our frequency is 40 kiloradians per second, and we have a capacitor, and its impedance is minus j over omega c, 1 over 40k, 5,000 picofarads. That turns out to be minus j 5,000. For the inductor, it's j omega L, j times 40k times 0.5 henries, and that's j 20k. My voltage source was a cosine function with an angle of 0 and a magnitude of 10. Write down my value of omega here just to remember that. The resistor is still a resistor, and here's my capacitor whose impedance is minus j 5k ohms, and my inductance, which is j 20k ohms. Step 2 is to do the analysis in the frequency domain. To find this current, I need to know what the voltage V1 is. V1 would be a voltage divider with our input voltage. 10 at angle 0 times this impedance over the sum of the two with the 5k resistor. So since I'm doing multiplication and division, let's convert everything to polar form. Of course, this is in polar form, so that's 10 at angle 0. This is going to be 5k at angle minus 90. And then putting this in my calculator, enter the real, enter the imaginary, and then hit two buttons to get the magnitude and angle. I get 7.07k, an angle of minus 45 degrees. Does the answer make sense? This is the hypotenuse, so it's got to be longer than either of these two. These are two equal lengths, so we're going to be at an angle of 45 degrees, but we're in the fourth quadrant because this is the real positive and the imaginary is being negative. That's exactly what it should be. The overall magnitude is 10 times 5k divided by 7.07k, and the angle is 0 plus a minus 90 and then minus a minus 45. Turns out to be 7.07 and angle minus 45. The current in here is going to be this voltage, 5V1, divided by the total impedance, which is 15k plus j20k. Okay, let's put this into polar form. This is really 5 at angle 0. V1 was 7.07 at angle minus 45. And then again, punching this in my calculator, I get a magnitude of 25k and an angle of 53.15. This is longer than either of these two, so that seems reasonable. We're in the first quadrant because these are both positive. This is longer than this, so the angle should be greater than 45 degrees in magnitude. And it is. Again, this could be wrong, but on the surface seems correct. We're going to multiply 5 times 0.707 divided by 25k. That's 1.414 times 10 to the minus 3. And I've got 0 minus 45 minus plus 53.15. That turns out to be minus 98.13. To come into the time domain and take the magnitude and then put the angle with the cosine of omega t. 1.414 milli times the cosine of 40k t minus 98.13, and the units are amps. And this is supplemental problem 4.3.